48 years ago, in the summer of 1977, humanity took a bold leap into the unknown. Two small spacecraft, Voyager 1 and Voyager 2, lifted off from Earth, carrying the dreams of a species eager to explore the cosmos. Back then, computers were clunky machines filling entire rooms, and space exploration was still finding its footing. The Voyagers were modest in appearance, metal frames, spindly antennas, and golden records etched with the sounds of Earth, but their ambition was colossal. Their mission began with a tour of the outer planets, a grand journey past the gas giants of Jupiter, Saturn, Uranus, and Neptune. Yet their true purpose lay far beyond. In a realm no human-made object had ever reached, the edge of the solar system, where the sun's influence fades and the vast interstellar void begins. Imagine these spacecraft as cosmic messengers, powered by tiny nuclear hearts called radioisotope thermoelectric generators, humming along through the vacuum of space. For decades, they soared through the darkness, their instruments peering into the unknown, their signals traveling billions of kilometers to whisper data back to Earth. Scientists waited patiently, knowing each message took hours to arrive, carried by radio waves moving at the speed of light. The Voyagers were on a quest to find the boundary of our solar system, a frontier where the sun's protective embrace meets the wild, untamed expanse of the galaxy. And when they reached it, what they found was nothing short of astonishing. This boundary, known as the heliopause, isn't a simple line in space. It's a turbulent, invisible frontier where two cosmic forces collide. On one side is the solar wind, a relentless stream of charged particles, protons and electrons blasting outward from the sun at hundreds of kilometers per second. This wind carves out a massive bubble around our solar system, called the heliosphere. Like a ship pushing through the waters of a galactic sea, the heliosphere stretches far, its leading edge extending roughly 3 times the distance from the sun to Pluto, with a long comet-like tail trailing behind. It shields our planets from the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between stars. On the other side of the heliopause lies this interstellar medium, a realm shaped by the explosions of ancient stars and the magnetic fields of the Milky Way. Here, the solar wind weakens, its strength no longer enough to push back the galaxy's influence. The heliopause is where these two worlds meet, a dynamic zone of chaos and energy, like the frothy edge where ocean waves crash against a rocky shore. When the Voyagers crossed this boundary, Voyager 1 in 2012 and Voyager 2 in 2018, they encountered something extraordinary, a region of searing temperatures, reaching up to 50,000 degrees Celsius, a phenomenon scientists poetically dubbed a wall of fire. But how can such extreme heat exist in the near vacuum of space, where there's barely any matter to carry it? And why didn't the Voyagers, made of metal and delicate electronics, melt into cosmic slag? The answer lies in what temperature means in this alien environment. In space, temperature measures the speed of particles, their kinetic energy as they zip through the void. At the heliopause, the particles are moving so fast that their energy translates to temperatures hotter than the surface of the sun. Yet, the interstellar medium is incredibly sparse, trillions of times less dense than Earth's atmosphere. Imagine a handful of superfast marbles scattered across a football field. Even if they're moving at breakneck speed, their rare collisions with a spacecraft transfer only a tiny amount of energy. The Voyagers, built to endure the harsh vacuum and temperature swings of space, sailed through unscathed, their instruments faithfully recording the drama unfolding around them. This fiery region isn't a solid wall but a consequence of a cosmic phenomenon called the termination shock. Picture the solar wind as a supersonic jet, racing outward until it slams into the denser interstellar medium. At this point, the wind slows abruptly, its energy transforming into heat, creating a turbulent zone where particles are energized to extreme temperatures. The Voyager's plasma detectors and cosmic ray sensors captured this shift, noting changes in particle direction and the composition of the medium. It was a moment of triumph, the first direct measurements of a boundary no human craft had ever crossed. But the surprises didn't end there. The Voyagers carried ultra-sensitive magnetometers, instruments designed to measure magnetic fields. Scientists expected the magnetic field at the heliopause to shift dramatically, aligning with the galaxy's magnetic structure rather than the sun's. Yet the data told a different story. When Voyager 1 crossed the heliopause, and later when Voyager 2 followed at a different point, tens of billions of kilometers away, they found the magnetic field just beyond the boundary was strangely aligned with the sun's magnetic field. This wasn't a fluke. Both spacecraft confirmed it. This unexpected alignment forced scientists to rethink their models of the heliosphere's interaction with the interstellar medium. It suggests the galaxy's magnetic field near our solar system is more intricately connected to the sun's than anyone imagined, hinting at a larger, more complex cosmic dance. These discoveries are more than scientific curiosities. The heliosphere is our solar system's shield, deflecting galactic cosmic rays, high-energy particles from distant stellar explosions that could damage spacecraft and potentially life on Earth. Understanding where this shield ends and how it interacts with the galaxy is crucial for astrophysics. It tells us about our place in the cosmos, how our star's influence shapes the space around us, and how we might one day venture beyond it. Every bit of data from the Voyagers, transmitted across a distance where a signal takes over 20 hours to reach Earth, is a treasure. These aging probes, now over 22 billion kilometers away, continue to send faint signals, each one a testament to human ingenuity and curiosity. The Voyager's journey has also paved the way for future exploration. In 2025, NASA will launch the Interstellar Mapping and Acceleration Probe, or IMAP, a mission designed to build on the Voyager's legacy. Unlike its predecessors, IMAP won't travel to the heliopause. Instead, it will orbit at the L1 Lagrange point, 1.5 million kilometers from Earth, where it can observe the solar wind and interstellar medium without interference from our planet's magnetic field. IMAP's goal is to create a detailed three-dimensional map of the heliosphere by studying energetic neutral atoms, particles born at the boundary where the solar wind and interstellar medium collide. These atoms carry clues about the heliopause's structure, revealing how our cosmic bubble forms and evolves. IMAP's mission is both scientific and practical. By mapping the heliosphere, it will help us understand how cosmic rays are filtered. By this shield knowledge that could protect future astronauts on long-duration missions, high-energy particles pose a real threat, capable of damaging electronics and human cells. IMAP's advanced sensors and spectrometers will also study how particles accelerate in space, shedding light on the physics of cosmic boundaries. Equipped with radiation-hardened electronics and a thermal control system to withstand the harsh environment of space, IMAP is like a cosmic cartographer, sketching the edges of our solar system's domain. The Voyagers, now drifting through interstellar with space, are humanity's farthest-reaching explorers. Their golden records, carrying the sounds of Earth music, greetings, and the heartbeat of a child, may one day be found by another civilization, a message in a bottle cast into the cosmic ocean. But their scientific legacy is immediate and profound. They've shown us that the edge of our solar system is not a quiet boundary but a dynamic frontier, alive with energy and surprises. The heliopause's high temperatures and unexpected magnetic alignments are windows into the forces shaping our cosmic neighborhood. As we stand on the cusp of new missions like IMAP, the Voyagers remind us of what's possible when we dare to explore. Nearly half a century after their launch, these small spacecraft continue to rewrite our understanding of the cosmos. Each signal they send back, faint and distant, is a whisper from the edge of the known, urging us to keep looking outward. The heliopause isn't just the end of the sun's reach. It's the beginning of a greater journey, one that invites us to imagine what lies beyond, where the stars beckon and the universe waits.